Okay, so I'm going to show you 6 different shapes, and I want you to try to tell me which one you think is different. So here's one. Okay. Here's a second one. Here's a third one. A fourth one. A fifth one. And a sixth one. I know some of these have different stick lengths, edge lengths, and some of them have different faces. But I'm hoping the one you saw as being different than the other 5 is this one. What makes this different is its faces are not all the same. It's got some triangular faces and some hexagonal faces. It's a nice geometric shape called a truncated tetrahedron, but it doesn't belong in the same group as the others. The other 5 all belong in the group known as the platonic solids. There are just 5 of them, these 5. And what they have in common is all of them have the exact same faces, congruent faces. In fact, they have 3 things. They all have the same edge length, so edge, 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 all identical. And all the vertices are exactly the same. These corners are all 5 edges coming together. And the faces are all the same, or congruent. They're all triangles. That's true here, that's true here. Here, the vertices are all the same, the faces are all squares, but they're all the same. This, all the edges are the same length, and all the vertices are the same, 3-way, but the faces are not. Hexagon, hexagon, triangle. The truncated tetrahedron belongs to a group of solids known as Archimedean solids, after Archimedes. We'll take that one out. These are just the platonic solids. I want to talk just briefly about some of the cool connections between them. Okay, the simplest clearly is this one, called the tetrahedron. It has 4 sides, and that's where the prefix tetra means 4. It also has 4 vertices, but that's not where the name comes from. The name comes from 4 identical faces. We shouldn't call them sides. Faces. Faces for a polygon. Faces for a polyhedron. We would talk about edges or sides for a polygon, like a triangle. Okay? One cool thing is the tetrahedron kind of stands alone. If I were to take the center of each face and use that to define the vertex of a new polyhedron, can you see how it would just be? I'll hold it right in there like that. Another tetrahedron, a smaller one, but still a tetrahedron. Okay? So I'm taking the center of each face and making that the vertex of a new one, and that would be the same thing, a tetrahedron. Okay? And by the way, just to show you, the tetrahedron's hypertile version looks like this. Now, that doesn't look a whole lot the same, but see the 3-way juncture? 3-way juncture? And there's 1, 2, 3, 4 of those. 1, 2, 3, 4 vertices. So, anyway, that's the tetrahedron. The octahedron and cube actually create each other when we do what we just talked about. Maybe it's easiest to see it with this one first. If I take the center of each of these 6 faces and use that to define the vertices of a new polyhedron, it would be right here, the octahedron. In fact, I can slide this in there and kind of show that. It sticks out. It could be smaller like the tetrahedron was, but it doesn't need to be. You can still maybe see that. And likewise, if I take the center of each of these, and there are 8 faces, so that's 8 vertices, you would get the cube. So these beget each other, if you will. And here are their 2 hypertile versions. This is the octahedron, and the reason that this kind of looks like a cube as well is because, again, these 2 shapes are related. If I focus on that yellow as being a face, there's the face, so that has 6 faces, but I'm not. The yellow is supposed to be one of the 6 vertices, and where 4-way come together like that. And this is very rigid, like this is, and like the tetrahedron, because it's made up of triangles, The cube, here's my cube. See, that is the square. It's got these three-way junctures, but again, that kind of looks like an octahedron, okay? So, and whereas this is very flexible, bendable, so is my cube. My cube can do things that these other structures can't do, okay? Finally, the last two platonic solids, this one, which has 20 sides and 12 vertices, is called an icosahedron. Icosa means 20. And this one, which has the opposite, ready? It has 12 faces and 20 vertices, is called a dodecahedron. Dodeca means 12. Okay? And yeah, pentagons, triangles. This one, very rigid. Yeah? And you ready to see the hypertile version of that? It's actually quite gorgeous. Boom. Okay? And if you're saying, wait, that looks just like the other one. It looks like this is made of pentagons. But again, this is not meant to be a face. It's meant to be a five-way vertex. And this has the same property as the cube and the octahedron. If I took, and this is harder to see, but if I took the center of each one of these triangular faces, you could probably see I've got a pentagon right there, so forth. Use those centers of all the faces to create a new polyhedron, it would be this, the dodecahedron, and vice versa. I could maybe fit that inside there. That would take some doing, but you could look up these connections. So here it is. Here is the icosahedron, and because it's made up of triangles, this thing doesn't budge. It's very firm. I did not bother to make this. Actually, I did make it, and it just loses all its shape because this thing distorts in ways that it doesn't make for a nice looking structure like this. So the dodecahedron hypertile, I'm not going to bother. You can certainly make one if you just follow the rules, and you'll find out it's very flexible and bendable, but it doesn't have that nice property of holding its shape at all. At least the cube still looks like a cube, even in its different permutations. It doesn't lose it that much. I was hoping to have something similar with this. No go. But I do have this neat thing, that this kind of serves as the hypertile version of either one of these. And look at these cool five-way pinwheel vertices. Okay? So, the 5 platonic solids, we've got hypertile versions for 4 of them, and the dodecahedron just not really that worthy of being built, just because it just doesn't look like anything. It looks like just a blob of tiles. Okay, go ahead and make it and see what I'm talking about there. Okay?